Today's lesson is on probability. Specifically, we'll be looking at sample spaces. The sample space is really just all possible outcomes, and sometimes it can get a little complicated to count the number of outcomes. So that'll be our focus for today's lesson. For theoretical probability, that's the number of favorable outcomes over all possible outcomes. Let's look at example 1. How many outcomes are in the sample space? List the possible outcomes. So our event, that's usually what's going on. We call it an event. Is you flip a nickel and a dime. So I'm going to teach you how to make a tree chart. So the way you do that is you put, maybe flip a nickel. That's the first part of the event. And then flip a dime. And you write that vertically. This is the way I like to do it. So for the nickel, I'm going to list all outcomes. There's a head and there's a tail. And I usually like to spread them out. And now for flipping the dime, there's also a head and tail outcome. But you put that under each outcome here. And you repeat it under each of the outcomes at the top. So now, as we list the all possible outcomes, I'm going to go head, head. That's one outcome. And the first H is for the nickel because that was on top, and the second head is for the dime. Now I have head, tails. That's another possible outcome. Then I have tails, heads, and then I have tails, tails. So this would be our sample space. There are 4 possible outcomes. Once you know the outcomes, it makes it very easy to do the probability. For example, later, if we were to say, what's the probability of flipping 2 heads if we flip a nickel and a dime? Well, that's 1 in 4, right? There's one way to get heads on both out of 4 possible outcomes. So later we'll look at the probability, but right now we're going to focus on listing the number of outcomes. And again, let me make that plain. There are 4 outcomes. And here we have listed all 4 of those outcomes. Now, let's list all the outcomes if you flip a coin and roll a die. So, here's our flip. And then we're going to have our roll. So I like to space them out nicely. You could get heads or tails. And if you roll a die, and a die is singular for dice, you could get a 1, 2, 3, 4, 5, or 6. And then I'm going to repeat that over here under tails. So now I could get heads and a 1, heads and a 2, and a 3, and a 4. These are all of the possible outcomes, and hopefully you see what's going on. And then we could also get a tails and a 1, tails 2, tails and a 3, tails and a 4, tails and a 5, tails and a 6. So notice we have 12 outcomes. And I didn't quite finish my tree diagram, but that's how that would look. An easy way to do this is to know there's 2 outcomes here, 6 here, and notice if you do 2 times 6, you get 12. So that's another easy way to count the number of outcomes. If you look at the previous example, there were 2 outcomes here, 2 here. 2 times 2 gives us the 4 outcomes that we ended up getting. So again, that's going to make it very easy. Now, if you roll 2 die, we could list all of those outcomes. There are 6 numbers on each So that's giving me 36 outcomes. And because we didn't want to list them all, just in the interest of time, here's a little picture showing you those outcomes. We have 2 die. Even if the dice have the same color, they are different. So we want to acknowledge that they are different. So you could get a 1 and a 1, a 1 and a 2. Notice that this one is different from this one, although, they both total 3. So as you start looking at probabilities, maybe you wanted to say, what is the probability that I'll roll a sum of 7? Well, there's 1, 2, 3, 4, 5, 6 different ways to roll a 7. So if we did probability, we could say there are 6 out of 36 ways to roll a 7, or a probability of 1 in 6 for rolling a 7. So with probability, there's a lot of different things we can calculate. For example, 2. Oh, did we write? Yeah, 36 outcomes. Wanted to make sure that was really clear. And that picture shows all 36 of the possible outcomes. Example 2, let's find the probability of a woman having 2 boys and 1 girl, any order, if she has 3 children. So now what we're going to do is list all of the possible outcomes. Okay? The first thing we're going to do is maybe look at the first child, the second child, and the third child. Let's do a quick tree diagram here. For the first child, she has an option of having a boy and a girl, or you could say male, female, however you like to say it. And then for the second child, boy and a girl. And remember, you list those under each. This is how you make a tree diagram. And then the third option, we have a boy or girl, and we're going to list those under each one here. And then I'll show you how we can list these possible outcomes. Probability, so much fun. So now, as we go through and list our outcomes, we start at the top, boy, boy, boy. That's one outcome. Then we can say boy, boy, girl. Then we can go boy, girl, boy. And then we have boy, girl, girl. This is a very organized way so that you don't miss any of your outcomes. Starting at the top, girl, boy, boy. Girl, boy, girl. Girl, girl, boy. And lastly, girl, girl, girl. So, notice we have 8 total outcomes. There was 2 choices here, 2 here, 2 here. If we multiply 2 times 2 times 2, we do see that there are 8 outcomes, and we have listed them. I like to multiply just to double check my count, make sure I haven't missed anything. Now we're ready to figure out the probability. This problem says we're looking for 2 boys and 1 girl. So let's see. Here's 2 boys and 1 girl. Here's 2 boys, 1 girl. Here's 2 boys and 1 girl. And I think that's all of the options. So the probability for having 2 boys, 1 girl, regardless of order, is 3 favorable out of 8 total outcomes. Or we could use a calculator and do 3 divided by 8, and we see that that's 37.5%. Sometimes we like to do it as a percent or even as a decimal. And all of these ways are acceptable. When you do a fraction, you must reduce. The probability of an event is the likelihood or chance that the event will occur. For example, you want to know what's the probability of me hitting the lottery? Well, I'll tell you what, it's going to be pretty close to 0, but not 0. And so I want to share with you a likelihood scale. If a probability is 0, we say that this is impossible. And if the probability is 100 or 1, if you were doing like a fraction, then we say it is certain. It is absolutely, without doubt, going to occur. Now here, my grandmother would always say that's just a 50-50 chance. But in math, what we like to say is that it is equally likely. Equally likely. Okay. Here, there's a lot of different words you can say. Probably not gonna happen, or not very likely. But it could still happen. This is kind of like where it's possible, kind of falls in. And this is more than likely. And here, this is like it's probably gonna happen. You can't guarantee it, but I'm pretty sure, So there's a lot of different words we could use in there. Plausible, falls into the not very likely category, Down here, you kind of say, well, it's rare, or probably not, it's possible, Okay, let's look at experimental probability. This is based on repeated trials. We call these trials experiments. So this is, for example, I say I flip a coin 10 times and 7 times I got heads. Well, that's experimental probability. Theoretically, we know that there's a 50-50 chance, so half of the coins should be heads and half of my flips should be tails. But that's theoretical. Experimental doesn't usually match. It can, though. Let's look at example 3. We have a spinner here, and this spinner, all 4 of the colors have the same area. Okay? Here are the results of an experiment. Out of 20 spins, 5 came up red, 7 came up green, 4 yellow, and 4 blue. If you add those up, you will get 20. The question is, for which color or colors does the theoretical probability equal the experimental probability? Well, what we want to do is we want to say there are 4 colors and they all had an equal space, and as long as the spinner is fair, meaning everybody had an equal chance, then 1/4 of those spins should be red, 1/4 should be green, 1/4 should be blue, and 1/4 should be yellow. So each color should have 5 spins, because 5 out of 20 would be 1/4. That's theoretical, and they should all have a 1/4 probability, which is saying 5, 5, 5, and 5. So therefore, red would be the one that the theoretical matches. So red, 5 out of 20 gave us 1/4, and that is what should have happened because it's one out of the 4 colors. So red